Imagine a single drop of liquid, clear and oily, resting on a tabletop. It looks deceptively simple, almost harmless, like a bead of spilled cooking oil or a dollop of thick syrup. But its placid appearance hides a volatile secret. When Italian chemist Ascanio Sobrero first synthesized it in 1847, he was so terrified by its power he called it pyroglycerin and warned against its use. This is no ordinary liquid. This is nitroglycerin, a substance so powerful and incredibly sensitive that the slightest shock can set it off. A gentle tap with a hammer, a sudden jolt, even a change in temperature can trigger a catastrophic reaction. It will explode with the force of a thunderclap, shattering the table and anything nearby. This extreme instability made it a nightmare to handle, a destructive force capable of immense and unpredictable chaos. And yet, this agent of chaos is also a tool that helped build our modern world. The very same chemical reaction that can level a building is used in microscopic doses to save lives by relaxing blood vessels and treating heart conditions. In larger quantities, it blasted tunnels through the Alps, carved paths for transcontinental railroads, and dug the foundations for skyscrapers and dams. To put its power in perspective, nitroglycerin is significantly more powerful, pound for pound, than TNT. While TNT is the famous military-grade explosive from movies, this unassuming liquid packs a much bigger punch. The key difference lies not just in raw power but in its form and stability. As a liquid, it's volatile and hard to control, whereas solid TNT is far more stable and safer to handle, which is why it became the military's choice. But for sheer shattering force, or brisance, nitroglycerin is king. So what happens during that explosion? It's a process of instantaneous transformation. When detonated, the liquid nitroglycerin rapidly decomposes into a massive volume of hot gas, mostly nitrogen, carbon dioxide, and water vapor. In a fraction of a millisecond, it expands to over 1,200 times its original volume. This near-instant expansion creates a supersonic shockwave, a phenomenon known as detonation. It's a blast of immense pressure moving faster than the speed of sound that can pulverize solid rock, twist structural steel into unrecognizable shapes, and send debris flying for miles. It's a sudden, violent, and almost complete release of chemical energy. Because of that incredible power, the incentive to control it was enormous. For decades, engineers and laborers risked their lives to use it. They could carve tunnels through mountains, clear pathways for railroads, and mine for precious resources deep within the earth. But the cost was terrifyingly high. Accidental explosions were common, claiming countless lives and earning nitroglycerin the nickname blasting oil. The journey from terror to tool wasn't easy, it was a deadly puzzle. How could humanity tame this liquid demon without sacrificing its strength? The answer wouldn't be found in brute force but in brilliant chemistry. It lies in understanding the atoms and molecules that give nitroglycerin its fury. The challenge was to find a way to stabilize it, to package its power in a safe, predictable form. A quest that would lead one man to an invention that would change the world forever. So put on your safety goggles. We're about to dive into the explosive science of nitroglycerin. Science rules. The story of nitroglycerin begins not on a battlefield but in a quiet laboratory in Turin, Italy. The year is 1847, a time when chemists were transforming everyday substances into materials of unforeseen power. Here a chemist named Ascanio Sobrero turned his attention to glycerin. This common byproduct of soap making was known for its use in lotions, but Sobrero, having studied explosives, suspected it held a more volatile potential. He carefully introduced the glycerin to a potent mixture of nitric and sulfuric acids. This process, known as nitration, generates immense heat. Sobrero knew that without constant cooling in an ice bath, the reaction would lead to a violent explosion. Every step required meticulous precision. From this chilled mixture, a new substance emerged, a dense, pale yellow, oily liquid. It looked deceptively harmless. He had synthesized for the very first time the compound he called pyroglycerin, which we now know as nitroglycerin, but his scientific triumph quickly turned to terror. This new liquid was shockingly unstable. When he heated a single drop, it detonated violently. A small amount struck with a hammer produced a deafening explosion, powerful enough to shatter nearby glass. It was dangerously sensitive to both heat and shock. The danger wasn't just explosive. In a moment of reckless curiosity, Sobrero tasted a minuscule amount. He documented a sweet, burning sensation followed by a violent, throbbing headache, the first person to experience its powerful physiological effects. Haunted by its destructive power, Sobrero became his discovery's staunchest opponent, warning it was too dangerous for any practical use. but word of an explosive far more powerful than black powder was impossible to contain, drawing the attention of industries like mining and railroad construction. The rush to harness its power proved catastrophic. Early attempts to transport liquid nitroglycerin were plagued by horrific accidents. It would detonate from the slightest jolt, from changes in temperature, or sometimes, for no discernible reason at all. A series of devastating explosions in the mid-1860s cemented its fearsome reputation. The world had a powerful new tool, but no one yet knew how to tame it. The person who finally solved the nitroglycerin puzzle was Alfred Nobel. Yes, the Nobel Prize's Nobel. A factory blast in 1864 killed several people, including his brother Emile. Driven by loss, he sought to tame nitroglycerin for safe, reliable use. He tried many approaches to reduce sensitivity without losing power: charcoal, sawdust, brick dust. According to legend, a leak showed that a fine, porous earth absorbed the liquid completely. Kieselguhr acted like a sponge, holding it in microscopic pores. The resulting putty-like mixture was far more stable. It could be dropped, shaken, even near a flame without exploding. It would only detonate with a blasting cap, precise, on command. In 1867, Nobel patented it as dynamite, from the Greek for power. He had tamed the beast. Dynamite reshaped industry, powerful, stable, and practical for construction, mining, and engineering. It made Nobel wealthy and propelled a wave of global infrastructure, ingenuity solving the impossible. For decades, the immense power of nitroglycerin was too volatile to control. With Nobel's invention of dynamite, humanity finally had a safe, reliable way to harness its energy. The impossible suddenly became possible. In an age of unprecedented ambition, engineers put dynamite to work on a monumental scale, embarking on projects that would literally reshape the face of the planet. Before dynamite, progress was paid for with grueling human labor. Armies of workers with pickaxes and shovels faced agonizingly slow and brutally dangerous work on projects like canals, tunnels, and railroads. Their primary tool, black powder, was a blunt instrument. It burned slowly, creating an inefficient push. Dynamite, in contrast, detonated, releasing its energy in a supersonic shockwave that shattered rock with focused, controllable power. This newfound control was a revelation. Using planned drill and blast patterns, engineers could fracture solid rock with surgical precision. Projects that once took years were completed in months, and ambitious blueprints became tangible realities. A key early triumph was the Gotthard Tunnel through the Swiss Alps. Completed in 1882, this 15-kilometer marvel connected northern and southern Europe, a feat only possible because dynamite could conquer the mountain's solid granite heart. Across the Atlantic, dynamite fueled America's westward expansion, blasting paths for transcontinental railroads through the formidable Rockies and Sierra Nevada. Without this power, connecting the coasts would have taken decades longer and cost countless more lives. The impact fueled modern growth. Dynamite cleared shipping channels for global trade, leveled ground for massive dams, and in burgeoning cities, blasted the deep foundations required for the first skyscrapers to rise. The mining industry was revolutionized. Dynamite allowed miners to reach previously inaccessible ore deposits, blasting through hard rock with unprecedented speed. The essential raw materials of the industrial age, coal, iron, and copper, were suddenly abundant. From roads and railways to the foundations of our cities, dynamite was the unseen engine of progress. It dug the canals, carved the tunnels, and mined the resources that built the modern world. It seems almost unbelievable that a substance famous for explosive power could help the heart. Early on, severe headaches were a clue to a medical secret. When absorbed, nitroglycerin releases nitric oxide. Nitric oxide is a vasodilator. It relaxes and widens blood vessels. Sudden dilation in the head can cause a throbbing headache. In the 1870s, William Morrell tested tiny, highly diluted doses on patients with angina pectoris. Within minutes, chest pain eased as more oxygen-rich blood reached the heart. Today it's a common treatment, often a small pill placed under the tongue for rapid absorption. The same substance can be poison or cure. Dose is everything. Topical ointments can improve local circulation and help certain chronic conditions. Studying nitroglycerin revealed nitric oxide as a vital signaling molecule in our bodies. That insight opened doors to modern cardiovascular therapies. Despite dynamite, nitroglycerin's story carries stark warnings. Oil well shooters worked in constant danger, moving unstable liquid over rough roads in so-called angel buggies. The Bath School disaster remains a somber reminder of malicious misuse and terrible loss. Reckless use of unstable explosives during railway construction cost many lives. Nitroglycerin-based chemistry underpins many smokeless propellants used in modern ammunition. Related formulations help power solid rocket boosters, lifting missions skyward. Nitroglycerin shows how science can turn danger into useful tools and life-saving medicine. With regulations, responsible handling, and respect for power, we learn, iterate, and improve safety. From a terrifying liquid to a builder of worlds and a saver of lives, science, guided by creativity and care, transforms danger into progress.